We'll be going over the ModelDB versioning system and how it can help you version your models. Many of these concepts may feel familiar to you, such as commits, reverts, and merges, and it's designed to comfortably enable not just reproducibility, but also better understanding and oversight over your machine learning development process. I'll be walking you through a series of notebooks here. They're available in our public ModelDB GitHub repository, and there will be a link in the description below. I won't go too in-depth on the specifics of the model or ModelDB's metadata logging. You can check our documentation and our other videos for that. I'm just focusing on the versioning components for now. So, a model is composed of a number of distinct ingredients. For example, the code that is written to build and or train it, hyperparameters that are used to configure it, the dataset it fits to, and the environment, Python or otherwise, that it's developed in. Here, I have a Python Jupyter notebook that's training a simple sentiment classifier with spacing. I'm working in a Git repository, and I'm training it on a particular set of English language tweets, negative and positive, for, say, 20 iterations. If I have these pieces of information, if I know that I have the same notebook in the same Python environment with the same data, then it should follow that I could reproduce this very model in the future. The way to capture these is by using our client's utility classes. This one picks up information about the notebook, its file path, and my current Git environment. This piece will keep track of hyperparameters, in my case, just the number of iterations. This captures metadata about my dataset on S3. And I'll also snapshot my pip environment, including the version numbers of all my Python packages. As you can see, we can capture all the ingredients we need fairly effortlessly, all in one place. Then we'll pull up a ModelDB repository and check out its master branch. Of course, the initial commit is empty, so we'll need to use commit.update to stage changes and, when satisfied, save it to ModelDB. Doing so will create a new commit on our master branch containing our updates. Now we'll be able to view our progress through the web app. As we can see in the tweet classification repository, we have these 4 items that I added just earlier. As an example, let's take a look at my dataset. This is a CSV that I have stored on S3, and as you can see, I now have a record of its bucket and key, its size, the last time it was modified, as well as a checksum I could validate against in the future. Once we have our model trained, with its training metadata logged to a ModelDB experiment run, we can also log our commit to that run. We'll associate specific blobs from our commit to this run. This is useful if the repository is involved in multiple different workflows, and it lets you highlight the relevant ingredients to the task at hand. Now that we've seen how easy this is, let's take a look at how powerful this is. Let's say that someone wants to build on our work and improve our model by using a different training dataset. Unfortunately, unbeknownst to them at the time, this dataset has a critical flaw. It only contains positive tweets. Nonetheless, same as before, diligent as we are, these changes get committed directly to master. Once the commit is saved to ModelDB, we can go to the web app to review what changes have taken place. Here, we'll see in our repository's updated history that our new commit has been added on top of master. And we can see the specific changes that it introduced, namely this new separate notebook and this new dataset CSV. Unfortunately, we may find that the broader Twitter landscape is not as positive as our dataset suggests, and so we need to revert this change. Fortunately, through our client, it's a simple 2-step process. First, check out master, this being the commit in question, and then use the revert method to create a revert commit on top of it that undoes this change. And once again, we can verify this visually through the web app by seeing our new commit on master, which has reverted its snapshot of the new notebook and flawed dataset, shown here in orange, in favor of the old notebook and the original dataset, shown in blue. Now that we've seen how reverts work, let's take a quick look at how to perform merges. This time, we'll improve our model in a different way by training a multilingual model with the addition of German language tweets. We'll snapshot both our English language CSV and our German language CSV as our dataset version. And as a good practice, this time we'll create a new branch called multilingual off of master. We'll save our commit to ModelDB with a descriptive commit message and take another quick look at the web app. We'll go ahead and switch the branch in focus to multilingual and verify that our new commit has been added to our new branch with the updated notebook and the additional dataset. When we're confident that our changes work as intended, we can proceed with merging this branch into master. To perform this to the client, we'll first separately check out master. Then we'll use the merge method to bring in the commits from our divergent multilingual branch. Now, one last time, we'll verify through the web app that master has been updated with the commits from our multilingual branch brought in behind this merge commit. And for definitive peace of mind, we can see that on master, the notebook has been updated and this new dataset has been added. This is how the ModelDB versioning system provides tools to help you reliably and responsibly version your models.